Hello, Jeff Disher here again. Today I'm going to talk about two-dimensional graphics, specifically compositors, which are the component that's used to combine multiple images on screen in, say, a window manager or just in graphics editing tools. So, first of all, this is going to involve going through the basics of what is a compositor. So I'm talking about the display controller, which is the component of the hardware which actually takes video memory and puts it on screen. So I'm talking about sprites, or as they're more commonly referred to in modern times, overlays. Blitter, both as it was represented in hardware and also software, but basically just what it does. GLES, which is the new OpenGL way of doing these things. And some talk about memory bandwidth, because that's sort of the interesting area of discussion when you look at modern composition or modern compositor implementations. So first of all, what is a compositor? Well, remember that the screen you're looking at is one actual element. It's just one two-dimensional piece of data. But that's not really how it starts. Internally, it's represented differently. You have things like multiple windows, which are all completely independent. And you also have other embedded pieces of information, such as cursors. You might have things like video that's coming in from perhaps directly from a webcam or just from a video file or streaming content on a website, or even OpenGL. You could actually be running something like a game in a window or some kind of similar piece of software that's just going to produce a single scene of OpenGL or 3D content, but you're actually going to have it embedded within the screen with all your other windows. The compositor is the component that actually combines all of these things into one output, that one screen element that you want to see. That's what the hardware will actually display for you. But the compositor is the software and or hardware components that actually put everything together from the original sources into that one piece of output. For example, these three windows are all completely independent, but the compositor knows how to put them all together into one scene. It knows that they've got things like an ordering. There's some that are in front of others, that hide parts of them, things like that. These are the areas that compositors worry about. So looking at the hardware from this, the display controller, it's the thing that actually does the drawing of the screen. So it does what's called a scan out from what we call a frame buffer. The frame buffer is just one big slab of memory that contains all the information that's going to go to the screen, all the pixel values. The scan out is just the order in which the display controller reads it. So this is just stored in memory, and the display controller reads it out. So it uses some memory bandwidth to do this for each frame. It's also worth noting that there's actually two frame buffers. Now there could be more than two, and historically there would be less, but two is generally the best way of looking at it from now. The screen is what actually reads the front buffer. That's what we call the buffer that's on the front of the screen, the one that you're actually looking at. But the compositor writes to what's called the back buffer. This is just another piece of information, another piece of data that's another image in the computer's memory. Now the reason why you do this is that you can be writing to the back buffer while at the same time, literally the same time, as the display controller is reading from the front buffer. This way you never end up having a problem of trying to read data that's currently in the middle of being written. Whenever the back buffer is finished being written, it'll actually swap with the front buffer. So that's how you get one frame followed by another. You're always writing to one that's on the back, and once you're done writing, you swap, and then you start writing again. Because now the front buffer has become the back buffer, so you can use it for your next frame. Sprites and overlays, which I'll talk about in a bit, those are added during the scan-out phase. So these actually do not go into the frame buffer. So, without further ado, sprites and overlays. Now, historically this is actually, well, even now, this is hardware that's used to add additional information to what's going to be on the screen during scan-out. But note, this is not information that's in the frame buffer. There could be reasons why you don't want to destroy the frame buffer with information. So, this was used a lot in, say, old games or game systems. You can see this in some old games or old game systems. If you have too many players on the screen at once or something, they'll start getting kind of staticky or kind of distorted looking, but the background won't. And the reason for that is that the background is actually the frame buffer. All of these little like players or power-ups or whatever floating around the screen, those are actually sprites that are added during scan-out. So if you have too many of them, the sprite hardware might not be able to keep up, and you might start missing parts of them. This was also used for the old text mode that you'd see on IBM PCs. of course, that way of using it was quite different. It essentially would give you a frame buffer in a very, very coarse way because of how they were using the sprite hardware. But basically, that's all it was. You just refer to a sprite, which happened to be a character in the video font sprite table. So today, though, we actually use these for a bunch of things still. For example, cursors. Like I've said, if where your mouse cursor is on the screen is actually being drawn into the frame buffer every time you move the mouse, well, what if the frame buffer content isn't actually changing? Now you still have to recomposite the frame buffer and swap it again and scan out the whole thing. But if you know the cursor is just something that moves around, that's not part of it, then you can just use that as a sprite or overlay. That way you don't have to change the frame buffer content, but this can move around and you can move it very quickly, and it will never require any additional operation to the frame buffer because the frame buffer is never being touched. These are only added when the content is actually going out to the screen directly. Sometimes for either an optimization or power savings, this is also used for things like video or OpenGL. You could actually say you have a screen which it has no content changing on it, but you're watching a video in a window right in the middle of it. Well, if you had to recomposite the entire screen for every frame of video, that's going to be 30 frames a second. That's a lot of composition, considering that nothing's actually changing. The entire background is staying static the whole time. So this way, why not just say, all right, well, we'll put the video somewhere else, and we'll just remember that that when we're actually doing the scan out, we get most of the background from the frame buffer, but except this one little rectangle here where we're going to put the video. So we'll actually scan out from the video there instead. That way you don't have to update the frame buffer for every frame of video. So it's either an optimization for performance because it reduces your CPU or GPU load, or one of the big issues is saves memory bandwidth and saves a lot of power because you don't have to do all that operation. On modern laptops and tablets and phones, this is a big deal. So getting on to how some of this actually is implemented and what the underlying kind of operations on the data actually are, we get to the blitter. Now this means bit level block transfer. And this is something that Commodore Amiga Incorporated introduced back in their computers some time ago, obviously. And basically the idea was that the CPU itself, when you try and draw multiple windows on screen, it would have to do all that fetching of memory and making decisions about which window you wanted to, which window was in front of which, how you build the output. This was really, really inefficient because it's very memory intensive. And also the comparison itself is very simple. So doing all this very simple thought process or kind of doing this very simple computation and decision making and a lot of memory bandwidth on the CPU is incredibly inefficient. The CPU is good at completely the opposite. It's good at doing things which are really complicated calculations using small amounts of memory. So historically, the blitter was something which was an actual piece of hardware they would use to do these composition phases. Basically, all it means is it was a way of combining bitmaps. So a bitmap in this case is, it's a general term, but for what we're looking at here, a bitmap represents a two-dimensional image. So the blitter would actually be able to combine those. Combining multiple bitmaps into one bitmap, that's what a compositor does. So this allowed for much of the composition of the screen to be done by this coprocessor that was being used in some of the computers and game systems at the time. In modern days, this has changed, but the idea actually still makes sense and still relevant. So how this works is there'd be times where you'd have to do things like make a complicated decision about what was on top and what was showing through from beneath it. Well, a lot of things don't actually have, like they're not just whole windows. You could have some sort of like pattern that's overlaying an image somewhere. So what you'd actually do is they had a very simple way of describing, okay, what's foreground and what's background in an image. So that way when the blitter was running over the image, it knew what parts to actually copy, because you didn't want to copy the background of the image you're trying to insert if you wanted that background to be effectively transparent. So they used a very, very simple concept called a mask. A mask would be just one bit for each pixel in the image, saying whether it was in the image or not. And the blitter would have a very, very simple decision to make when running over these. So it could know how to add one image into another, specifically avoiding its background, because of this very simple concept of the mask. In fact, if you look at a lot of the way a lot of images are stored today, a lot of them still use the same idea. They still have a dedicated mask. More often, you're seeing images that are stored with what's called an alpha channel, which is actually a way of describing which parts of the image are transparent. It's more effective than a mask because you can describe it being a whole range of different transparency values as opposed to just being visible or invisible. But a mask is very, very fast on very simple hardware. So that's why it was used before. So yes, the problem is, the limitation here is that there's no transparency. So this specific idea is typically not used anymore, but the idea of how this was put together was very common and very important. And of course, because of how all this works, the software blit, as I mentioned, is not something the CPU is good at. So writing in software is not very good unless the software is actually running on the graphics processor, which typically is better at doing things like this because the graphics processor is kind of an evolution of the blitter. So that brings us to how we do this now, using the actual OpenGL, the 3D hardware that we have, and the OpenGL hardware that we have, and the GLES programs that we can run on it. Now, if you're not familiar with that, this just means OpenGL embedded systems. Essentially, it's just a, basically you can think of it as the language of the graphics processor. It's a bit more complicated than that. Basically, that's what it comes down to. This is how you can describe to the graphics processor what you want it to do. So it allows you to write programs that actually manipulate data on the graphics card itself, or it allows you to describe how you want a shape to be structured in 3 dimensions. It allows you to put things like data that you want it to be, that you want it to use on shapes that it's going to draw, and those images are called textures, which is something that is quite important for this area. So now modern compositors use GLES because, like I said, the graphics processor is kind of an evolution of the blitter. So it makes sense you'd use this new hardware to do it, but modern GPUs are programmable, and they can allow for things like multiple levels of transparency. So this is how you'd implement it today. You actually will write a GLES program that will run on the CPU that is the compositor operation. So that way, all you have to do is you put all your content that you want into your windows or whatever, and then you'll actually copy those into graphics memory as GL textures, which is just the name that GL uses for its 2-dimensional images, and other things too. In general, that's what we're interested in now. So this means that the GPU itself is now free to copy the visible textures into the frame buffer. So the GPU actually is building the frame buffer in modern hardware, so it makes sense that you'd actually run the program to do the composite on the GPU as well. It already has all the data. It already controls the output location. So this is great. It means that you can do very complex compositing operations, and the CPU doesn't do any of it. All it does is describe to the GPU and the OpenGL system where the windows are and what content is on them, and it figures out how to actually position them all and what they would look like when they're combined in the way that's described to them. This is also really useful in that, say you have something like video or OpenGL content that you wanted to composite into the screen. Well, if you weren't using the GPU to actually do the composite, you'd actually have to take the video or the OpenGL, which in many cases is already going to be in the graphics memory because it was the one that produced it, copy that back out, do some slow operation on the CPU, and then copy it back in the window. Doing it in hardware, just doing it in the GPU means that you never have to do that back and forth. All this information already exists in the GPU. All you have to do is describe the order in which to combine things. And the hardware will do it for you without using the CPU. So that's how things are implemented now, and that sounds great. So what are the current problems? Why are people still building these? Why is graphics composition not a solved problem? And it really comes down to memory bandwidth, like many things do in the modern age. So the point is that the GLES compositor uses GPU bandwidth. This is great because, say if you have things like a dedicated graphics card that has its own memory on it, that memory is fast, it's usually laid out in a way that's optimized for this kind of operation, copying and manipulating large chunks of image data, because that's basically all the graphics card does. So it's going to be really fast for this. And also it's discrete, meaning that it's actually completely distinct and disjoint from the system memory. So your CPU can be using system memory to do whatever it wants while the GPU is actually doing the compositing operation. These things happen completely in parallel. And they can because they're in completely different memory spaces. They don't get in each other's way at all. Where this becomes a problem is when you look at integrated graphics with shared graphics memory. This is very common in things like cell phones, tablets, laptops, and low-end desktop machines. Historically, these integrated graphics processors were kind of frowned upon because they didn't have the computational power to do things like a lot of complex 3D rendering. And while that's still true compared to their dedicated counterparts, one of the bigger issues with them these days is that they don't actually have the memory bandwidth of the dedicated counterparts. It means that since they share the same memory as the CPU, it means that now when you're running your compositor on the GPU, it's playing in the same sandbox as the CPU is. When it's trying to manipulate data to produce the output frame buffer from using the same shared system memory, now the CPU has to wait, or the CPU has to be slowed down, or something like that, because it's now got too many things going on using the same memory. So this is a limitation there, and it's why there's still a lot of work being done here, because the GPU and the CPU will compete for the memory bandwidth. Remember, this is not quantity of memory. That's an issue, but that's different. This is the memory bandwidth. It's how quickly you can access it. So now we have too many components trying to access the same chunk of memory. Physically, it's one thing. Even though you could have multiple channels that allow you to look at various parts of it at the same time, it would be faster if one component had complete dedicated access to all of those resources. But because there's going to be sharing, these are competing for the resources, so it'll slow things down. And you'd think that, well, computers have got so much faster, why is this still a problem? Well, look at what we've been doing recently with screens. Screen resolution is becoming really, really high lately. So that becomes a problem because more pixels is more memory, a lot more memory. So this is something that is still happening today. And this is still an area of a lot of real development because it's not a solved problem. And it's actually an interesting problem because there's lots of interesting opportunities with the hardware that's provided. So to look at how this is all together, and this is going to assume that you're using a discrete graphics memory system, not a shared memory system like a tablet or something. This is going to be like a high-end desktop workstation, that kind of thing, just to make it clear how this works. So in the system memory, you're going to have, you'll be drawn to a bunch of windows. Note, it is possible that the windows are actually produced by a similar kind of compositing operation or a sort of a meta compositor, but I'm going to ignore that right now. That's just an optimization idea that's possible for people to do, but to understand how it works is not required. So in this case, we'll say that the windows themselves are being drawn to in normal system memory. So then when you want to actually draw them, or you want to say, okay, I'm finished updating this, what you're going to do is copy these into GPU memory. So when they get copied in, we call them a texture because they're now in GL, they're now a GL concept. Say we have other information too, like maybe there's a texture we produced from an OpenGL scene that we're rendering on the GPU as well. Well, that's great. Now we've got these three things together, so we can actually begin blend to make the frame buffer. So we describe the location of the windows that we want, and we tell the GPU, okay, here's where the windows are, here's what their ordering is, here's what their transparency is. Now go and generate the frames. And what we get is something like this. Now you'll see in this example, I've actually demonstrated how you could have one of those textures be semi-transparent. The blue window here is not fully opaque. You can see things like the OpenGL scene through it. And this is fine, because the GPU knows how to do that kind of semi-transparent blending operation. So this is something that's really common these days. It's how most modern compositors work. They've been going that way for probably about 10 years. If you go back to around 2000, 2001, they didn't really do much of this, but today pretty much everything works this way. So it's interesting because they're still improving this, there's still ideas for how to make this better. So, and because we keep adding more pixels to the screens, the problem's getting harder to solve. So it is really neat because they're still doing so much. So I thought that was interesting. If you have any questions or comments, either comment on the video here or send me an email at jeff@jeffdisher.com. And I hope that I'll hear from you, or I'll put together some videos going forward, some new demos for some open autonomy stuff coming through, also some other ideas of things I just wanted to talk through, which I thought would be interesting. Anyway, thanks for watching.